November 2011. The Yamal Peninsula, Arctic Russia. A drilling platform stands alone on the coastal tundra. Night operations. The temperature has fallen below -22 Celsius, and dawn is still hours away. At 3:17 in the morning, the drill stops. Not a mechanical failure, not a seismic event. The nearest seismograph registers nothing, flat line. But the ground beneath the platform has shifted 14 centimeters in 40 minutes, sideways, silently, without a single tremor, without anything pressing on the surface above. The engineering team logs the incident. They classify it as a thermal anomaly, not a structural failure, not a warning. The next morning, they resume drilling. The question is not why the ground moved. The question is how anyone builds a tunnel through a material that behaves like that. The Yamal incident was not unique. By the standards of Arctic construction, it was not even unusual. What made it remarkable was the documentation, a rare moment when the numbers were recorded precisely enough to mean something. 14 centimeters, 40 minutes, zero seismic activity. The team filed the report under thermal anomaly because that was the accurate category. The ground had not cracked, it had not collapsed. It had simply moved. The way a very slow, very cold fluid moves under pressure. The borehole was intact. The platform was intact. The incident was, officially, within operational parameters. And that classification, calm, administrative, almost indifferent, is where the real problem begins. Because the central question of Arctic tunnel engineering is not whether the permafrost will move. It will. The question is how a structure can be built through a medium that behaves like a pressurized, viscous liquid, and then expected to hold its shape for 50 years. That is not a rhetorical question. It is a structural engineering problem that has been actively managed and actively obscured for decades. Permafrost covers 65% of Russia's land surface. It underlies 25% of all land on Earth. The layer ranges from 15 meters near its southern edges to 1,500 meters in the Siberian interior. To grasp what that number means at a single drilling point, stack the permafrost beneath one location in central Siberia, vertically above the surface, and it would reach the height of 4.7 Eiffel Towers, placed end to end, pointing straight up into the sky. That is the medium through which engineers build tunnels. The material is not simply frozen soil. It is a composite, mineral particles, organic matter, liquid water, and ice, bound together in a structure that holds only within a narrow temperature window. At -2 degrees Celsius, permafrost sits at the boundary of instability. At -15, it reaches what engineers call a conditionally stable state. The difference between those two conditions is 13 degrees. 13 degrees separate a load-bearing material from one that begins to flow. Now consider the drilling process itself. A standard Arctic rig generates between 80 and 120 kilowatts of thermal energy per meter of penetration. That heat radiates outward into the surrounding ground. Within a radius of 8 meters from the borehole, soil temperature rises by 3 to 5 degrees, not over years, during the drilling operation itself. The act of building the tunnel degrades the very medium the tunnel depends on. And when drilling ends, when the lining is installed and the equipment withdraws, what exactly holds the structure in place? The answer involves a phenomenon called thermal creep. Under sustained mechanical load, the ice crystals inside frozen soil do not remain static. At temperatures well below zero, in conditions that feel, to the human body, like solid ground, those crystals begin to deform. They flow, not quickly, not dramatically, but continuously, without interruption, for as long as the load is applied. The permafrost does not break, it moves. The Severomuysky Tunnel in Buryatia is the longest railway tunnel in Russia. 15 kilometers bored straight through the Severomuysky Ridge, part of the Baikal-Amur mainline. Construction began in 1977. The schedule called for 7 years. It took 26. The tunnel opened in 2003. December 1984. A senior geotechnical engineer named Viktor Razbagin was conducting a routine inspection at section kilometer 8.3. The concrete lining had been poured 6 weeks earlier. His measurements showed the lining had displaced 22 millimeters from its installed position. 22 millimeters in 6 weeks. He filed the observation. The construction team did not stop work. The official project journal recorded the movement as settling within acceptable parameters. The acceptable deformation tolerance for that class of structure was 5 millimeters per year. The actual rate at Razbagin's section was 44 millimeters per year, nearly 9 times the design limit. The journal entry read, "Within norm," and the work continued. What the Severomuysky case illustrates is not a failure of engineering knowledge. The mechanics of thermal creep were understood. The relevant literature existed. What it illustrates is something more uncomfortable: the gap between what the instruments record and what the official documentation acknowledges. That gap has a second dimension. The tunnel itself, once operational, becomes a permanent heat source. Ventilation systems run around the clock. Trains generate friction and exhaust heat. Electrical systems radiate energy into the surrounding rock. Each year, the permafrost adjacent to the lining absorbs enough additional thermal energy to raise its temperature by 0.3 to 0.8 degrees Celsius. That warming is not reversible. Once permafrost thaws past a critical threshold, it does not refreeze under operational conditions. The zone of thermal degradation expands outward from the tunnel wall, year after year, without interruption. Which raises the question of what the official safety assessments for these structures actually say. In 2018, the Siberian branch of the Russian Academy of Sciences, specifically the Institute of Permafrost Studies, published an independent geological survey of the Severomuysky Tunnel corridor. The findings were precise, methodical, unambiguous. The rate of permafrost degradation measured from the tunnel's central axis, 1.2 meters per year, advancing outward into the surrounding massif. The active thermal influence zone, the area where ground ice content and structural integrity had been measurably compromised, extended 34 meters from the tunnel wall. The original engineering design had calculated a thermal influence zone of 12 meters. 34 meters versus 12. Not an estimate, not a projection. A measured value produced by independent instruments, published in an academic geological journal. During the same period covered by that survey, the official operational reports published by Russian railways described the tunnel's geothermal condition using a specific phrase: stable geothermal state. Not a single public document released by the operating authority acknowledged that the active degradation zone had crossed the design boundary. Not one report quantified the discrepancy between the projected 12 meters and the measured 34. The phrase stable geothermal state appeared in each annual report, without qualification, without notation, without reference to the Institute's published data. The Severomuysky Tunnel is not decommissioned. It is not under emergency review. As of 2024, it operates on its standard timetable. Freight trains pass through it every day. The structure's design service life is 50 years, calculated from the year of opening. That timeline ends in 2053. Two numbers remain without comment: 34 meters versus 12. And a single phrase: stable geothermal state, printed in reports that the Institute's survey directly contradicts. The numbers sit side by side. They occupy the same space. They do not agree. The Severomuysky case is not the story of a tunnel that failed. It is the story of the distance between what instruments measure and what official language describes, and of how quietly that distance can grow, year after year, beneath a structure that carries loaded freight trains through a mountain range in Siberia. 34 meters of degraded permafrost, 12 meters on the engineering diagram, 22 meters of ground that no public document acknowledges. If one tunnel contains that gap, documented, measured, published in a peer-reviewed geological survey, and absent from every operational report, then a simple question follows. How many other infrastructure projects built through permafrost, through unstable formations, through environments that move 14 centimeters in 40 minutes without registering on a single seismograph? How many of those structures are operating today with an equivalent distance between what the ground is doing and what the official record says? The Severomuysky Tunnel is not the only structure of its class. It is simply the one where someone measured carefully enough to publish the difference. The next case is larger. The gap between the official version and the engineering reality is wider, and the structure in question carries something other than freight. That is the subject of the next video.